Hey guys, welcome back. So, we just think we might have just made a observation that may or may not lead to a discovery. So we're looking at these main bearing caps and, you notice that this one looks different, right? Obviously it doesn't have the bolt holes. But then, this is the one where this is a 01 through 05, so this is where the thrust washer goes down here. And one thing I noticed is this cap looks wider. Let me, get the light going. See what I'm talking about. If you look at this one, you can see this ring kind of goes all the way around. When you go to that one, you see it stops. You go to this one, it stops, and you go to that one, it kind of stops. But not so on this first one. So we've already measured these other ones. So look at this. It's hard to get a caliper in here, but these are about 0.78. Yeah, there it is, 0.78. These are about 0.78. Anyway, come look at this one. When you go to the one for the thrust bearing, sorry for the light messing this up, but these are bigger. This is like 0.87, something like that. So this is a thicker cap. The question is, I guess they did that because the thrust washer is thicker, and it looks like it creates like a lip. I'll try to get the camera in there so you can see it. Yeah, so it's kind of like creating that lip that the thrust washer hits, and that probably stops it from spinning. Well, that's fine. But the immediate question is the crankshaft different to allow this thicker, thrust washer and bearing to fit? Because if it is, if they modified the crankshaft to clear that, I won't be able to beef any of these other caps up. But what if they didn't? What if they're all the same, the crank's the same? It's possible that there's room to thicken up these caps. So we're about to explore that and see if there's anything to it. Okay, so I said we're going to explore it. So by explore, I've actually got a crankshaft here. So what I'm doing, I pulled these bolts out that hold the caps in, and we're about to knock these caps loose, and we're going to wipe the bearings clean, and I'm going to unpackage. I got a crankshaft that's all wrapped up. We're going to unpackage it and throw it, just drop it in here, and start looking around, see if I don't have a set of feeler gauges here. I don't know how this is going to go, but we're going to try to roughly measure this and see if there's any chance of making these caps wider, because that would, if possible, that's some like low-hanging fruit to make something stronger. Okay, got all this cleaned up. About to grab the crankshaft and set it in here. Alright guys, so we just threw the crank up on frankly, my desk. Probably shouldn't be on a desk, but we did it. And we're about to check this thing out. So this is the back of the crank where like the flex plate goes, or the flywheel or whatever. That's that first main bearing cap. You can see it's got like a small little machine surface there. We go to the next one. This is where a thrust washer goes. You can see it's much taller. It's like that on both sides. That's where your thrust washer makes contact. So all the other bearings, they have a little spot, but it's not as pronounced. You can see each one of these has one, but it's not as wide. Same thing on the front. So question is this wider? Let's find out. Okay. Roughly, let's see, try to get this is a caliper measurement. It's not really perfect, but let's go with 0.948. It's pretty close. That's kind of hard to get in there. Alright, it's hard to get this caliper exactly up in here, but it does look smaller. Getting about 928. So maybe 20 thou smaller. Let's see if we can do this one. Kind of hard to measure, much less do this one-handed. By the way, I did get a tripod ordered. Thank you, Mr. Subscriber that recommended that. I'm sorry I can't remember how to say your name. But that was a great idea, and I do have a new one coming. So yeah, this is showing like 928. So it looks like they're about 20 thou narrower. But here's the thing. So this is the one that the main goes on. Yeah. This is like 860 something, and the other one, we know that one was like not that big. Yeah, like 0.78. So there's a difference here. We may be able to fatten these up a little bit to get some extra strength. That is interesting that, from the factory that one is a little bit wider. Alright guys, so we just checked this out. So we measured the width of this journal here where the thrust washer goes. We measured this one, which is presumably the same on all of them. Guess I should check that. So up here, here's what we got. So for regular main, the crankshaft, the gap on the crank is 928, whereas where the thrust one goes, it's 948. So it looks like they did trim a little metal off the crank, narrowed it up a little bit, gave it some more clearance. Okay, so it's a little bit bigger of an opening, so you would expect the cap to be bigger. And the cap is bigger, but look how much bigger. We go from a 782 to an 868. So that's 86 thousandths difference. You know, they made this cap, they gave it 20 thou more space, but they didn't just make it 20 thou wider, they made it 86 wider. So that's interesting. So what works out, the one where the thrust goes, the bearing cap, so we're not talking, so I'm saying this is the one the thrust washer goes on, but the cap itself is not designed to touch the crank. You know, by design, that's what the thrust washer does. So you have to have adequate clearance between the cap. So on this cap, Mazda gave it 80 thou of clearance. Okay, so 80 thou. So if that thrust washer starts to wear out, this bearing would hit first. We know that. And we know that because all the others have way more clearance. At least the one next to it does. I'll measure them all and make sure they're the same, but I bet they're all the same. So what is the advantage of doing this? Because I can't think of any. I mean, I guess you have a known point of where it's going to fail, but I mean, if your thrust washer is running in, you know, if you've done that, I mean, you've trashed that bearing before anything's going to hit. So I'm thinking this is an opportunity to beef this up. I guess I need to look at it a little more, make sure I'm not missing something else, but I mean, it seems like I can just make this cap wider. So I guess I'll look at the block next and see if there's any differences in the block. But what I'm seeing is the difference between these two numbers. So that's 46 plus 20, so that'd be 66 thou. I mean, that's over, you know, that's about a 16th of an inch. It looks like I can make the caps wider without any penalty. That's what it looks like. And so if you guys saw the previous video, we only made the cap 10 times stiffer. I mean, you know, time to step up our game, right? So if we use this math right here, we'll be able to beef up these caps a little more and get some more strength out of it and increase stiffness. So here's the thing. So right now the caps are, I think, 782. So if we go, this kind of works. So if we go 782 and we add the 66 thou, that would bump them up to 848. So if we divide that by our original dimension, we're adding another 8.4% to that number. So if we were 10 times, you know, stiffer before, and we multiply that by the new change, we have a syntax error. But anyway, if you do that, you're going to end up with 10.8. So now we're looking at almost 11 times stiffer. So that's a big difference in stiffness. And it looks like this is just free. The material I'm going to buy is going to be thicker anyway, so that's not going to matter. And if you just, you know, if you machine less metal off, that's actually cheaper to make, because it costs money to cut metal off of stuff. So this could be a awesome benefit. There may be, like I said, maybe I'm missing something. Maybe there's another reason I can't do this, but I haven't found it yet. And it looks like this is just a freebie. Man, it sure pays to, well, like I said, unless I missed it, but it sure pays to go digging and try to really look at everything, because it looks like now we're going to be able to beef these caps up basically a free 8% in stiffness. So with that number that was 10, we'll be able to bump up to, like, actually that number 10 that I said yesterday, I didn't do the math, but it's probably closer to 11. So now we're probably looking at going from 11 to 12 times stiffer. So we're getting some huge gains here. And man, how about that? So anyway, I guess the only notable thing is that the caps would be different thicknesses. Since the crank has a different clearance here, since this number here is a little bit bigger, and we're probably going to maintain clearance, we're going to change what Mazda did and make all these the same gap. So that means we will have to have this one cap will be, you know, a little bit thicker than all the others. But yeah, how about that? Looks like we just found another way to improve this. Alright guys, so we've been looking at this and taking measurements, and I got a buddy of mine named John. He's he works at the company I work for, but he used to be a machinist for years and years. He's pretty damn knowledgeable about how to machine stuff. And he knows, so I have this mill, it's this little baby mill that I converted to CNC, and he's concerned I'm not going to be able to cut 4140 very well at all with that machine. So, and he brings up a good point. This machine's, you know, it's cut steel parts, but a lot of the stuff it's made is aluminum, and I usually go kind of slow. So if I'm going to make these, I kind of need to find out if the machine's up for the task. So what I'm about to do is I'm going to head up to the shop and we're just going to start cutting on some metal. And I have a big chunk of round bar that's something. I don't know if it's like 4140, 4340. It's something like that. I don't even know what it is. I'm going to see if it's written on it by chance. But we may try that because I remember I tried to cut it one time and it was hard to machine. I know I have some steel and I know I've got aluminum for days. So we're just going to go up there and cut on some stuff and try to understand the limits of the machine. So, we're sitting here trying to design parts, but we got to be able to, we want to make our own parts. So we got to find out what we can do. Is this machine even going to be capable? I've never cut 4140 on this machine. Probably the worst I've ever cut is just hot rolled steel and a bunch of like 1018 steel, cold rolled. So we're about to go up there and start cutting on some aluminum and steel and maybe some alloy steel and just see what happens. Get a feel for what our capabilities are. So another thing worth noting, I have this software. It's called HSM Advisor. So this software. So I've got a software already that does like your CAD and your CAM, but when you're setting up your CAM, you have to tell it that's computer-aided manufacturing. You can basically create tool paths and G-code to do your CNC machining, but you have to tell the software, say some of the basics like how big is the cutter, how many flutes are on the cutter, how far does it poke out, things like that. But then you also tell it things like how deep of a cut do you want to make, how wide of a cut do you want to make, what RPMs do you want to spin, on your spindle, which is how you figure out like your chip load and feed per tooth and things like that. So what this software does, I paid for this and it's only like you have to pay every year or something. I don't know, it kind of sucks. It's not like a one-time forever. But anyway, this software, you can go in and tell it like, hey, I'm cutting this alloy metal. Like it's got a whole drop-down list of, different materials. And it's got some basic info. So you tell it roughly, I got this end mill, I got this material, and it'll kind of give you some recommendations, and then you can tweak stuff, and it'll like you can go in here and say, well, I don't want to run as much depth of cut. Like when I click this, see how it turns green? When I click these, it gives me like recommended values, and you see down here I've told it what the horsepower and torque limits are for my machine, and it's basically just maxing that out and saying, well, use that depth of cut, that width of cut, spin this RPM and go that fast, and that'll end up putting the machine right at its limit. And that would give you, according to this, almost 2 cubic inches a minute of metal removal rate. Now that would be totally hauling ass. Typically when I run this machine, it runs at like 0.1. So that's like 20 times faster than I normally go. And to be honest with you, I really doubt the machine can even do that. But that's the thing, is we don't know. And typically when I make parts, I can't afford to scrap something. I can't afford to break an end mill or break the material. And especially as you get further into a part, you don't want to scrap it towards the end because then you got to start all over again. So what we're going to do is we're about to go test some of this. Now, some of it's obvious, like when the machine starts squealing and shaking and, bad things TM. So there's a point where it's bad. But what we're going to do is we're just going to go run it, do some test cuts, start ramping up on, different parameters and just kind of see what works. Get a feel for this thing and then get an idea for what these limits are. Because if we understand, like say we did a bunch of cutting, we're going to keep the data. So basically we're going to do some tests. And we're going to kind of write down like, okay, we did this and this was the result. And we're going to go back and plug the numbers into this after the fact and see what horsepower and torque was coming up. And what I'm guessing is there's going to be like a torque limit where it's like, hey, just don't go above this torque or it doesn't work. And there's also probably going to be like a feed per tooth and RPM correlation. Because what I've noticed on this machine in previous experience is this machine's happier when you run it at higher RPMs and less torque. And that has to do with basically you're not asking the machine, since there's less torque, it doesn't have to be as rigid. And higher RPMs just kind of helps because, again, it's not rigid. So I'm betting the trends will show something like that. But we're going to track it and kind of find out what works and then run it back through the software to gain some insight. And then hopefully this will be like an iterative process where once we have some data and we run it through here, that'll give us some insight into what works. And then we can use that to come up with better, feeds and speeds and RPMs and all that, and then test it again. So, about to head to the shop. Alright guys, that'll do it for this one. So in the next episode, you'll see us, we're going to head to the shop and we're going to start cutting on metal. I'll show you how that goes. Till next time, y'all take it easy.